Time does not stop as described in relativity theory. This theory was designed by Albert Einstein when he designed special relativity theory. His conclusion then was the speed of light is constant and matter cannot exceed light speed. But 1925 Erwin Hubble discovered the universe is expanding. It is important to clarify one point. While you feel weightless in space, your mass is not zero. Weight is a measure of gravity pulling on you. In orbit, you are in freefall, so your weight is zero. Yet the gravity of spacefield expansion as a universal gravity is greater than the speed of light. So, weightlessness and expanse acting in the spacefield gravity would allow faster than light propulsion by itself. Quantum physics cosmological expanse framework regime structure. Figure 1 presents the quantum physics cosmological model expressed as a sequence of distinct expanse field regimes, replacing a single relativistic expansion law with layered spacefield dynamics. The longitudinal axis represents cosmological time, while the radial widening denotes decreasing spacefield density and increasing expanse velocity. Regime 1, exponential inception regime. The universe originates from an exponential inception event characterized by ultra spacefield density. Expansion is dominated by intrinsic vacuum expanse rather than energy-driven matter motion. Conventional relativistic speed limits are not yet defined in this regime. Regime 2, superluminal expanse regime following inception. The spacefield enters a superluminal expanse phase, in which the expansion velocity of space exceeds the speed of light without transporting matter locally faster than light. Lorentz invariance remains valid within local matter frames. While the global expanse field operates under higher speed geometric dynamics. Regime 3, structure stabilization regime. As the spacefield density decreases, gravitational coherence zones emerge. Matter condenses into stabilized regions where Newtonian and relativistic mechanics apply locally. This regime enables the formation of bound systems while remaining embedded within a globally expanding expanse field. Regime 4, galaxation regime. Galaxies and large-scale structures form within semi-stable expanse layers. Local gravitational dynamics dominate over expanse forces at galactic and subgalactic scales, while intergalactic separation continues to be governed by the expanse field. Regime V, present expanse regime. The current epoch is characterized by low-density space-field conditions and accelerating expanse behavior. The expansion is increasingly dominated by vacuum and zero-point field effects rather than matter density. Regime 6, superspeed future expanse regime. Speculative in the far future domain. The spacefield may enter a superspeed expanse regime in which expanse velocities vastly exceed relativistic limits. Matter-bound regions become increasingly isolated, and the expanse field approaches vacuum dominance. Regime 7, multiversal expanse domain. Hypothetical at extreme expanse field dilution. Branching expanse domains may emerge, representing independent spacefield continuities rather than conventional parallel universes. This regime is speculative and represents an extrapolation of quantum physics field behavior beyond observational limits. In this framework, relativistic speed limits apply to energy and matter within stabilized regimes, while the expanse field itself operates under a higher-order geometric speed hierarchy unique to quantum physics. Ever stare up at the night sky and feel a sense of wonder? It feels endless, right? Well, what if I told you the universe isn't just vast, it's getting bigger every single second? This isn't science fiction. It's one of the most mind-blowing truths of cosmology. Let's rewind to the early 20th century. Most scientists, including the great Albert Einstein, believed the universe was static and changing, eternal, and fixed in size. But then, an astronomer named Edwin Hubble made a discovery that changed everything. He was observing distant galaxies, and he noticed something strange. Almost all of them were moving away from us. And the farther away a galaxy was, the faster it seemed to be speeding away. Imagine baking a loaf of raisin bread. As the dough rises and expands, every raisin moves away from every other raisin. From the perspective of any single raisin, it looks like all the others are rushing away from it. That's what's happening to our universe. The dough is space itself, and the raisins are galaxies like our own Milky Way. Space isn't an empty stage where things happen. It's an active, dynamic fabric that's continuously stretching. This is the core of the cosmological expanse theory. It tells us that the universe began in an incredibly hot, dense state that Big Bang and has been expanding and cooling ever since. It's not that galaxies are flying through space, but rather that space itself is expanding, carrying the galaxies along for the ride. So, what does this mean for the future? Will the universe expand forever? Will it eventually slow down and collapse back on itself in a big crunch? Or will the expansion accelerate until everything is torn apart in a big rip? Scientists are working hard to answer these questions, studying mysterious forces like dark energy, which seems to be fueling this cosmic acceleration. The universe is not a quiet, still painting. It's a dynamic, evolving masterpiece, and we are lucky enough to have a front row seat. Every time you look at the stars, remember you're witnessing this grand cosmic expansion in action. Thanks for joining me on this journey through space and time. If you enjoyed this, hit that subscribe button for more cosmic explorations. See you next time.